9 is about nicotine. And what we learned in the background information is that nicotine is a liquid at lower temperatures, and it's actually soluble in water. In part A, we're asked to use an observed freezing point to calculate the molality of the solution. So we need to consider the Vant Hoff factor before we jump into our calculation. Nicotine is covalent. You can look up the formula or the structure, and you're going to see that it consists entirely of nonmetals. So because it's covalent, the Vant Hoff factor is going to be equal to 1. So I wrote down my freezing point depression equation, and I left off I because it's equal to 1. Delta T of F is going to be the absolute value of the observed freezing point. So in here I'm going to put negative 0.450 degrees Celsius. Kf, since this is an aqueous solution, I know I'm going to use 1.86 degrees Celsius per molal, because that's the freezing point depression constant for water. And then my unknown is that molality. Put that in blue. I need to isolate the molality, so I'm going to divide each side by 1.86 degrees Celsius over molal. Then I'll see how the units cancel. So degrees Celsius cancels with degrees Celsius, leaving with molality, and that needs to go up to the top. And so when I crunched those numbers, I got a molality of 0.241935. So I'm actually going to use the whole value. It's a little bit longer in my calculator. I'm actually going to use the whole value in the next part of the problem. If the problem were to end right now, just in part A, I would say that I have a molality of 0.242 molal. I would round to 3 sig figs. In part B, we need to use the information from part A to calculate the molar mass of nicotine. We're given some additional information as well, such as the mass of nicotine that was used in the preparation of the solution and the mass of water that was used. So I know that molality equals moles of solute over kilograms of solvent. So I'm plugging in my molality that I obtained in the previous part, in part A. And here is the mass of the water in the denominator. I already converted it to kilograms. So I'm going to just cross multiply those two things. And I wound up getting 1.18355 times 10 to the negative 2 moles of solute. With that information, I can calculate the molar mass. I always like to think of the units of molar mass when I'm doing these types of problems. So molar mass has units of grams per mole. So I need to take the grams of solute and divide by the moles of solute. So I have both of those. I'm going to put the 1.921 grams in the numerator and the 1.18355 times 10 to the negative 2 moles in the denominator. And at the end of the day, I got a really reasonable molar mass of 162 grams per mole. Since we've been working on freezing point depression and boiling point elevation problems, it's important to remember that those things are known as colligative properties, which means the identity of the solute isn't important. All that really matters is how many moles of particles does that solute form. So in order to account for the disassociation, the creation of additional moles of particles, we use what's known as the Vant Hoff factor. You already know that for covalent compounds, since they don't disassociate, your I value is going to be 1. Your Vant Hoff factor will be 1. Now, what you need to be on the lookout for when I is not going to equal 1 are your ionic compounds, strong acids, and weak acids. The strong acids are listed here. There's 6 of them. And with the strong acids, we're going to assume 100% dissociation, just like we do for our soluble ionic compounds. So something like sodium chloride, we assume that it breaks up into 2 pieces, sodium cation and chloride anion. And so our I value for sodium chloride then is 2. Same thing would happen with hydrochloric acid. Weak acids are where it gets a little bit trickier because they don't dissociate completely. Only a small percentage of the weak acid molecules will dissociate. But we'll get to some calculations there. What you'll see in the lab, if you get to do some of these labs in real life, that what you write down on paper. So for instance, sodium chloride on paper seems like it should have an I value of 2. But it doesn't quite get there. It gets close. It's like 1.95 or something like that. But what that lower value tells us is that some of the sodium chloride compounds, even though they dissolve and they disappear, they don't really break apart, which is something interesting to think about. One of the formulas that we can use to help us get at the I value is this one that I wrote right here. It's something that I kind of came up with to kind of wrap my head around what's going on. And it works. It works all the time. So you're going to take the number of moles of particles, or the number of particles that are in that aqueous solution, and divide by the number of moles of dry particles. So before you put those particles in there, how many would you have counted? Or how many moles of that would you have counted before you stirred it in? So let's look at this example together. There's 6 red cations and 6 blue anions. And because there's a 1-to-1 ratio between the two, it leads me to believe that there was 6 compounds in the dry form. So I'm going to put a 6 on the bottom of my equation here to solve for I. Now in solution, there's 12, and we can just physically count them. So I'll do 12 divided by 6, and that gives me an I value of 2. Let's work on analyzing I a little bit more by looking at these beakers and what's going on in there. Here we have a weak electrolyte. And so whatever was dissolved in there, whether it was an ionic compound or a weak acid, didn't dissociate all that much. So its ability to conduct electricity is limited. It will conduct electricity a tiny bit because there are some ions in there, but not as much as our previous example. So I counted up what was going on in the beakers. So we had 2 red cations and 2 blue anions. In addition, we had 4 undissociated particles. So these right here, 1, 2, 3, 4. They show me that there's a 1-to-1 ratio. And with the 2 red and the 2 blue, I'm thinking that that used to be 2 undissociated particles. So altogether in the dry form, like if I connect these back and imagine how they were before, I would have 1, 2, 3, 4, 5, 6 particles or 6 compounds in the dry form. However, when they're mixed in solution, 1, 2, 3, 4, 5, 6, 7, 8, they broke into 8 pieces. So the I value for this weak electrolyte here is 1.3, to repeating 3. So 1.33333. This one, what is this? I don't know, maybe it's a covalent compound. It looks like it hasn't broken apart at all. And that's a really easy case to handle, right? Because when something doesn't dissociate, the number of particles in the dry form will be the same as the number of particles in solution, and a 1-to-1 ratio, and we're just going to get an I value of 1. Problem 10 is this really cool conceptual problem. We're to treat it like a multiple choice problem. So they're asking us which one of the following solutions will have the highest boiling point. They all have the same concentration. So what we need to focus on is how do these different compounds dissociate in water. So the first one, C12H22O11, well, those are all nonmetals. So I'm going to label that as covalent, and then I can say my I value here is 1. Sodium chloride forms 2 ions, the Na plus and the Cl minus. So the I value here is going to be 2. Similar analysis of magnesium chloride, it breaks into Mg2 plus and 2 chloride ions. So the I value over here is 3. So looking at all 3 of our options, I would say magnesium chloride is going to have the highest boiling point because it has the highest I value. So as I was writing number 10, I was a little bit bothered by the fact that they all had the same concentration. How are you going to analyze a situation, the same question, but when your solutions have different concentrations? So that's what I set up down here. I would still start by identifying the expected I value for each of the 3 solutions. So hydrochloric acid breaks into 2 ions, so it's going to have an I value of 2. Barium nitrate breaks into 3 ions, it's aqueous, soluble. So its I value is going to be 3. And then C12H22O11 is a sugar, it's covalent, so its I value is 1. If it was like the previous problem and all the concentrations were the same, then I would pick the barium nitrate. But now we also have to consider the impact of concentration. I know they gave us molarity here, and we're used to thinking about boiling point elevation and freezing point depression in terms of molality. However, we don't really need to solve, and we don't have enough information. We don't need to solve for the actual change in the boiling point. Rather, I'm going to focus on what is the impact of molality and the Van Hoff factor together. But since I don't have a molality, I'm going to just multiply the molarity times the Van Hoff factor to kind of get a feel for the impact of the 2. So here I'm going to do 2 times 2. So my impact would be 4. Here it's 1 times 3. So the impact of concentration and Van Hoff factor is 3 for the barium nitrate solution. And then for the sugar, it's 5 times 1. So it's a little bit of an unexpected result, right? Because of the high concentration of the sugar solution, even though it's covalent, we would expect the highest boiling point with this one, because it has the highest impact between the both. So problem 11 asks us to calculate the freezing point of an iron 3 chloride solution. It's aqueous. Interestingly enough, they do give us a Van Hoff factor of 3.2. So we're going to use I equals 3.2. However, we think about iron chloride, we would expect it to break up and dissociate into an iron 3 plus, and then 3 individual chloride ions. I would expect an I value of 4. So this I value of 3.2 tells me that the iron chloride doesn't dissociate 100%. Some parts or, some whole compounds stick together. It's just not breaking up all the way. So plugging and chugging over here, I'm going to do 1.86 degrees Celsius per molal because it's an aqueous solution. I'm going to use the 0.10 molal that they gave us, and then my I value of 3.2. At that point, I got a value of 0.5952. And if I check my units real quick, molal cancels a molal, and so I'm just left with degrees Celsius there. Be careful on multiple choice, that's not your final answer. They asked us to actually calculate the freezing point. So you always do the pure, unadulterated freezing point. So we're going to do, since this is water, we're going to do 0 degrees Celsius minus 0.5952. So your pure one minus your delta T of F value, and then we get negative 0.5952 degrees Celsius. In question 12, we're given some information about two different weak electrolyte solutions. In this first one, they tell us that it's a 0.050 molal solution and that the freezing point is slightly below 0. The part that they left out that's really critical to solving the problem is the identity of the solvent. How did they prepare that solution? So I kind of threw in the AQ over here so that we can assume that it's our solvent's water. That's critical because our freezing point depression constant is based on the solvent. Let's plug and chug. So for delta T of F, we're going to use the absolute value of that in these equations. So I'll put 0.0986 degrees Celsius over here. And then we have 1.86 degrees Celsius per molal. And then our molality, which is 0.050 molal, times I, which is our unknown. And I want to isolate I, so I'm going to divide each side by 1.86 degrees Celsius divided by molal times 0.050 molar. Alright, so we do want to check how units are canceling on these. I is a unitless constant. I haven't really emphasized that enough in the introduction, but I is unitless. And what we see here is that molality cancels with molality, and degrees Celsius cancels with degrees Celsius, and that leaves us with no units and an I value of 1.06. So for problem 12b, they give us quite a different set of information. It's almost concerning, right? They give us molarity, and then they start talking about the hydrogen ion concentration and nitrite ion concentration when the weak acid disassociates. And it's like, what are we going to do with that? How are we going to use that information to calculate the Vant Hoff factor? So what came to mind was this formula that we worked on earlier when we did the beaker problems. So we know that the ratio of the moles of the particles that are actually in the solution divided by the moles of the particles before you put them in the solution will give you your Vant Hoff factor. How can we work this? So I'm using molarities over here, but if I'm assuming like 1 liter, then the molarity and the moles are interchangeable. So if we have 0.100 molar, and that nitrous acid starts to break up, we know that it's going to form equivalent amounts of H plus and nitrite, which I wrote down here. But then what happens to the 0.100 molar? So it breaks into two things, but we're going to lose this amount from the original. So in order to get the amount of the undisassociated acid in solution, I did 0.100 molar minus 6.91 times 10 to the negative third molar. And that gave me this 9.309 times 10 to the negative 2 molar value here. So what's all in solution? In this solution, we expect this amount of H plus, we expect this amount of nitrite, and then cross this one out. We expect this reduced value of the weak acid. Now, coming over here then, the moles of the particles in solution. I'm going to do 6.91 times 10 to the negative third, plus that, plus that. So I have to add up all three. And when I did that, I got 0.10691. And And again, if it bothers you that I'm doing this in molarity, then you can write moles. We can just assume that it's 1 liter of solution, divided by what was happening before. So before, it was just 0.100 molar. And then when I divided those two things, I got an I value of 1.0691. It's unitless. Probably 3 sig figs here because of the 3 sig figs with both values. So for nitrous acid, I would report an I value of 1.07. You've noticed on both of these problems that weak electrolytes, whether they be weak acids or compounds that don't disassociate 100%, it's okay. The I values can be super close to 1 because they're only disassociating to a really small extent.